So as usual, we'll go ahead and start out with unsigned, and let's go ahead and start with addition. Now, with unsigned addition, to the final product here, the actual result, all we're going to do is add up the two numbers that we're adding, and we'll end up with a true sum. Now, here's the thing. The true sum of whatever we're adding might actually have an extra bit, right? Because if we think about it, let's just assume a little 4-bit representation. If we add 1111 and 0001, well, we're going to end up with 10000. But if we're only dealing with 4-bit word sizes here in this example, well, we don't have room for that, do we? So what we end up doing with unsigned addition is discarding the carry bit. We've overflowed the space that we have available for this particular representation, so we're just actually going to ignore the carry. So what that does is actually implements modular arithmetic. If we want to take a look at the math for what this actually does for us, is to give us the result of u plus v mod 2 to the w. So if w in our example is 4, then 2 to the w is 16. So it's actually going to give us u plus v, which is 16, mod 16, which of course is 0. So that's the mathematical basis for how this works. But basically in the code, in the bits, just dropping off the carry bit ends up performing this operation. Now, that's how the standard addition function operates. There are implementations where you could actually take that carry bit and move it around to the lowest significant bit and add it back in. But that's not how the standard function works. And we can actually see this by doing a little code demonstration. So what I've got here is just a little demo file that I banged out here to show you what this looks like in code and how it acts. So we can see over here I've included stdio because I do want to print my results out, and I've included limits.h, which we mentioned in a previous video. Now in my main here, I've just declared some unsigned integers, ux for unsigned integer x, unsigned integer y, and the result will just be unsigned integer that we'll call UR. So UX I'll set to the maximum value for an unsigned integer, and UI will just set to 1. So when I add those two together down here on line 16, well, we should get uint max plus 1, but what we'll see is that we'll end up with a result of 0 because we've filled up our representation that we have available. When we add 1, we're going to get a new one. We'll have a carry bit of 1 and then just followed with a bunch of zeros, and this is going to implement that modular arithmetic that we just mentioned. Then we'll just print out the results. I know that there are nicer ways than putting a few \n's in here to format it nicely, but this is just a little demo thing. So when we add ux and uy, we end up with ur, so let's just see what that does. So I will go ahead and compile this, and then when we run it, we find out that this says, aha, adding, well, this big old thing, that's our maximum unsigned integer, and 1 yields, it yields 0. So we just demonstrated that standard addition is what happens when we just add things together in C. Now let's take a little bit of a more visual look at what this means for us. How does this change when we go from mathematical integer addition without the limits that are placed on us by representations in a computer system to what happens when we're actually doing unsigned addition in C? Well, for mathematical integer addition, if we've got 4-bit integers u and v, we just compute the true sum. And I mean, as we've seen before, if we plot this out in 3 dimensions, we'll just see a nice plane here, right? As u gets bigger, the value gets bigger, and as v gets bigger, the value gets bigger. And this happens in a linear way in both directions, so we just end up with this nice plane that we see here. The difference is, if we're dealing with unsigned addition in a computer system, well, we can overflow, right? If we end up going beyond our representational limits, then we loop back around to 0 because we're doing that modular arithmetic. So if the true sum is between 0 and 2 to the w, not inclusive, right? If it's less than 2 to the w, then we're fine, right? It acts just as we would expect it to act mathematically. However, once we get to 2 to the W or above, we have that overflow. So it just drops right back down to 0. So in this case, for the same range of values for U and V, we actually end up with 2 planes, right? We're going to have a certain amount that, as long as we're within those 4 bits for our result, we're fine. Everything's going to act just like we expect it to. But once we get above that and we have a carry bit, it overflows, drops back down to 0, and we kind of start all over again. Well, now that we've addressed unsigned addition, let's take a look at how does this change when we switch over to 2's complement. And the good news is it really doesn't at the bit level, right? 2's complement addition and unsigned addition have identical bit level behavior. Right? We just add up those bits in a bitwise fashion. If we have a carry bit, we discard it, just like in unsigned addition. So when we take a look at a little snippet of C code, if we declare S, T, U, and V as ints, well, if we actually just do a cast of U to unsigned and a cast of V to unsigned, add those up together and then cast them back to 2's complement, it works exactly the same as just taking T and adding U and V directly as 2's complement numbers, right? The S will be equivalent to T because we do the same exact thing. It just goes right back to same bit level representation. We just interpret it as 2's complement instead of interpreting it as unsigned. So this changes the evaluations that we get out of the back end, but the actual initial procedure of just adding up the bits and discarding any carry is the same thing. So, as we might expect, when we visualize 2's complement addition, we end up basically just adding another plane, right? Because we're going to add more wraparound in case we overflow. So if the sum is greater than or equal to 2 to the W minus 1, it becomes negative at most one time, because we can only ever end up with one carry bit potentially with a simple addition. And if the sum is less than negative 2 to the W minus 1, it becomes positive, again, at most one time. So we just end up with 3 of these planes instead of the 1 that we would expect mathematically or the 2 that we get with unsigned addition. Now, the big takeaway here, though, is, again, let's just keep it simple. When we're doing addition for either unsigned or 2's complement, all we have to do is just add up those bits, just throw out the idea of how we're representing it, add up the 2 different bit patterns, throw away any carry, and then interpret it however we're interpreting it. If we're interpreting it as unsigned, we interpret it that way. If we're interpreting it as 2's complement, that gives us a different numerical output, but it's the same exact thing going on at the bit level. Now, with multiplication, there are really no surprises. Our goal is to compute the product of 2 W bit numbers, right? Whatever our word size is, we've got 2 numbers that are represented in our word size. We want to compute the product, and signed or unsigned, it doesn't really change that much. Now, the thing is, with multiplication, we can have way more than one carry bit, right? And actually, for both unsigned and 2's complement, we can actually end up with 2 times W bits. So if we're talking about 4-bit word size, we could actually end up needing 8 bits to represent exact results. There's some math here to show you that, but with unsigned, right, our product can be anywhere between 0 and 2 to the W minus 1 squared, which ends up meaning we need 2 times W bits to represent that. For the 2's complement, the min ends up being a little bit more complicated on the math, but the short story is it can take up to 2 times W minus 1 bits, and for 2's complement maximum, if we actually took T min and squared it, is the only time we'll run into this, but that can take 2 times W bits as well. So the takeaway is, for both 2's complement and unsigned, you might need twice as many bits to represent a product as you do to represent the 2 numbers that you're multiplying together. So in order to maintain exact results, we'd have to keep expanding the word size, right? Every time we do a multiplication, we would have to double our word size, basically, to be safe. Now, There are packages called arbitrary precision arithmetic packages that can do this in software if you really need to, but let's talk about the standard approach. Well, happily, this is a very familiar process for us. In unsigned multiplication in C, instead of just dropping a carry bit, we'll drop the high order W bits. All right, so if we do a true product, we end up with 2 times W bits total. We just drop the higher order W bits. This implements modular arithmetic, just like dropping the carry bit implemented modular addition with unsigned. So that's very familiar to us, right? We do pretty much exactly the same thing. With signed multiplication, again, we're just going to ignore the higher order W bits. So if we set aside effectively 2 times W bits for our product, we set aside the high order W bits and drop those and just keep those lower order W bits just like we do with the other. Now, something to be aware of, because when we're dealing with 2's complement, we're dealing with multiplication of potentially negative values, some of the higher order W bits might be a little bit different than what we get for an unsigned multiplication, but that kind of doesn't matter because we're dropping them anyway. Those lower bits, the lower W bits, are going to be the same, so we do the same thing. Right? We perform our operation, we drop our higher order W bits as opposed to just dropping the carry bit like we do in addition, and we interpret as we're going to interpret, whether it's unsigned or 2's complement. Same idea. Perform the operation, drop the higher order bits, interpret it however we're interpreting it. Now that we've covered those basics, let's talk about some fun stuff that we can do to save some clock cycles. First of all is a power of 2 multiply with a shift. So instead of actually doing a multiplication, let's see what we can do just by doing shifts, right? Which we talked about in the last video. So if we do some unsigned integer u, and actually this works for both signed and unsigned. So if we just have u as our input and we shift it to the left, k places, that actually gives us u times 2 to the k. So if we think about it, if we just have 0, 0, 0, 1, and we shift it once to the left, we're going to end up with 2. We've multiplied by 2 to the 1. If we shift it twice, we end up with 4. We've multiplied by 2 squared. This works no matter what we're dealing with, so we can actually do this to kind of shortcut things for ourselves. So a couple examples. If I want to multiply by 8, instead of actually doing multiplication to do u times 8, I can just left shift u by 3. That's going to give me u times 2 cubed, which is u times 8. I can even combine shifts and adds or subtracts to multiply by values that aren't actually exponents of 2. So I can do u left shifted by 5, right? That's going to give me 2 to the 5th, 32, minus u left shifted by 3, which is u times 8, right? So 32u minus 8u ends up being 24u. So I can do u times 24 by doing 2 shifts and a subtraction, which in a lot of cases will be faster actually than just doing a multiplication. Most machines shift and add or subtract faster than they can multiply. So your compiler will generate this code for you automatically. This is a compiler optimization that we see all the time, but we want to keep in mind that this is the kind of thing that's actually happening at the bit level. When we call a multiply, your compiler might actually be turning that into a series of shifts and adds or subtracts rather than using the more expensive operations. Now we can do the same thing just in the other direction to divide with shift by a power of 2. Right? So we want to get the quotient of an unsigned by power of 2, right? We're going to divide by some power of 2. We can just write shift, and we're going to use a logical shift. Now, what that's going to give you is u divided by 2 to the k, but we're going to take the floor of that because we're dealing with integers, so we don't get to have fractional values, right? Remember when we talked about shifting, With integers, at least, we drop off the stuff that kind of goes off to the right. Now, when we take a look, we have our two operands, right? So our 2 to the k is going to be where we'll shift to the right by k, and we'll use a logical shift. Keep in mind that there's a difference between logical shift and arithmetic shift, and this is why we kind of focused on that in a previous video. So go back and review that if you don't remember how that works, but we want to keep in mind that when we do a power of 2 divide with a shift, we're going to use a logical shift. So we take those operands and we shift everything over. We shift u over by however many places k gives us. And we'll have some stuff past the binary point. So u divided by 2 to the k could potentially give us fractional values, and that's a problem when we're dealing with integers. So that's why we take the floor, and that gives us our final result. So this table down at the bottom just kind of shows you what this looks like. If x is 15,213, right, then we're not shifting it at all. We're just leaving it alone. So obviously the computed value will be 15,213. And we see the binary here at the last part of it. Now, if we right shift it by 1, right, we are dividing by 2, and that gives us the expected result. If we just did mathematical division by 2, 15,213 divided by 2 is 7,606.5. Once again, though, we don't have fractional values to work with when we're dealing with integers. So we take the floor of that and we get 7,606, which, as we can see in the bit pattern, it's just the bit pattern shifted over to the right by 1. If we shift by 4, we're dividing by 2 to the 4th, or 16. Which mathematically would give us 950.8125. Again, we have to take that floor because we're dropping off the stuff that goes out past the binary point. And binary point, it's the same as decimal point, except when we're dealing with binary, we call it the binary point. So our computed value, when we get it into an integer representation, is 950. And once again, when we look at the binary representation, we've just taken the initial x and shifted it by 4. That gives us our division by 16. So we can do these things to save those clock cycles. We can make things run a bit faster by keeping in mind the mathematical properties of what shifting these bits around does for us. So let's summarize and take a look at the basic rules that we always want to keep in mind when we're dealing with arithmetic and integers. For addition, unsigned or signed, normal addition is followed by a truncation, right? The same operation on the bit level. So you just add and then truncate that carry bit. For unsigned, addition is a mod to the 2w, right? Mathematical addition plus the possible subtraction of 2 to the w. So signed, it's a modified addition, mod 2 to the w, to result in the proper range. So mathematical addition plus the possible addition or subtraction of 2 to the w. So this is where we get into that modular arithmetic, and that's why for unsigned we have those 2 planes, and for signed we have the 3 that we saw on the visualization slides. With multiplication, for both unsigned and signed, it's a normal multiplication followed by the truncation, so same operation on the bit level. For the unsigned, it's a modular arithmetic thing. It's multiplication, so the product of the multiplication, mod 2 to the w. For signed, it's the modified multiplication, mod 2w, right? It results in the proper range, but it's a little bit modified because remember, those higher order w bits might be a little bit different than we get with an unsigned multiplication. But once we truncate those, once we chop those off, those lower bits are going to be the same. So when all is said and done, it kind of ends up looking the same.